All right. What I'd like to do to start off here is to write the electron configuration for the entire first column of elements in the periodic table. So I'm going to write them out here. Hydrogen with an atomic number of 1. So we'll just put a 1 right there. All right. And then below that, lithium with an atomic number of 3. I'll put there. Sodium below that with atomic number 11. And then potassium below that, atomic number of 19. Rubidium with atomic number of 37. And below that, cesium with an atomic number of 55. And we might as well go ahead and do the last one, francium, with an atomic number 87. Now, so we could categorize it this way. How many electrons do each of these have? Well, the atomic number, which is written down here in the bottom left of the symbol, is the number of protons. The number of electrons will be equal to that as long as we're dealing with neutral atoms. When we get talking about ions, where electrons are gained and lost out of an atom, then the atomic number won't equal the number of electrons. But in this case, we'll assume neutral atoms. So the number of electrons, hydrogen is 1, for lithium it's 3, for sodium it's 11, for potassium it's 19, rubidium is 37, cesium would be 55, and francium 87. Now what I want to do is draw the electron configuration for each of these. All right. Now the electron configuration we get by filling in an Aufbau diagram. For one electron like hydrogen, we would put a single arrow here representing the electron. We usually start with them pointing upwards, all right? So it would look like this, 1s, and then there would be a little up arrow there, okay? Now, that gets to be a tedious method of writing electron configuration, so we condense that a bit, and we don't signify the electron with an arrow. We just simply write the number of electrons in each of the orbitals as a number that's a superscript on the orbital type. So for hydrogen, it's 1s1. Right. Now, how about lithium? 3 electrons. Well, 2 of them will go into the 1s, and the third one will go into the 2s. So it'll be 1s2, 2s1. 1s2, 2s1. All right. Now, for sodium, 11 electrons. All right. 2 of them would go here. 2 of them would go into the 2s. And then into the 2p's, we're able to stuff in 3 pairs. Remember, the p orbitals come 3 to a group. 2 electrons in each orbital, so that'd be 2, 4, 6. That'd be a total of 10 electrons. And then the 11th electron would go into the 3s. So it'd be 1s2, 2s2, 2p6, 3s1. Right. 1s2, 2s2, 2p6, 3s1. All right, good. Now potassium, element number 19 electrons. All right, 1s, so there'd be 2 there, 2 there, 6 there, 2 there, 6 there. How many total is that? 2, 4, 6, and then another 6 here would be 12, and another 6 here, 18. The 19th would be into the 4s orbital. So it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So let's write that out. 1s2, 2s2, 2p6, 6, 3s2, 3p6, 4s1. Alright. So let's go ahead and do rubidium. Now rubidium's got 37 electrons. Let's just start filling in the orbitals. All right. Now, of course, you're going to have the exact same configuration, you know, all the way up to this. So let's do that. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then what comes after 4s? Well, it looks like 3d does, but let's go here and just look at this method of figuring this out. After 4s, right, 3p, 4s, we come up 3d and then 4p. 3d and then 4p. How many electrons does a d orbital, how many electrons is a set of d orbitals able to accommodate? All right. A d orbital is able to hold 10 electrons. All right. S's could hold 2 electrons. P's could hold 6 electrons. D's could hold 10 electrons. And F's could hold 14 electrons. All right. Remember that these s orbitals come as singles. So an s is a single orbital. Each orbital is able to hold 2 electrons. All right. P orbitals come 3 to a group. 3 orbitals per group, if you will. Each of the 3 orbitals is able to hold 2 electrons, so 3 times 2 is 6 electrons. D orbitals come 5 to a group. 5 orbitals to a group. Each of these orbitals holds 2 electrons, so 5 times 2 is 10 electrons. And F orbitals come 7 to a group. 7 orbitals to a group. Each orbital holding 2 electrons, so 7 times 2 is 14. It's a good idea to remember this. Okay. So anyway, getting back here, 4p6. Now, how many electrons total is that? 2, 4, and then 6 is 10, 12, 18, 20, 30, 36. So I need only one more electron. What comes after the 4p? Well, if I look at this, after the 4p is the 5s. It'll be 5s, and then I only need a space for one more electron. So if I count up all these little tiny superscripted numbers, 2, 2, 6, 2, 6, 2, 10, 6, 1, I get 37. So that's the electron configuration for rubidium. And cesium. Cesium's got 55 electrons. So we're going to start 1s2, 2s2. It's going to be the exact same as the one above it. We just have to add to it. 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, then 5s2. So that's going to be what, 38 electrons. That's one more than this one, 38. So I have to go beyond that. So after the 5s is the 4d. It'll be 4d10. So that's what, 48 electrons. I'm just going to put a little reminder here, 48 electrons, okay? And after 4d comes 5p. So 5p6, that'll take us up to what, 54 electrons. And I only have to put one more in there, right? So what's after 5p? After 5p comes 6s, so it's be 6s1. Let me get rid of that. Okay. You know what? I think I'm going to get rid of francium here. We're going to end up not being able to fit it onto my little board, so we'll just skip it. I think I'll be able to make my point. All right. remember what I did was to choose all of the elements in this very first column of the periodic table. All right, let's go take a look at the electron configurations. Actually, the very last entry of the electron configurations for each of these. Well, for hydrogen, here we go, it's 1s1. For lithium, the very last orbital filled is the 2s, and it has 1 electron. For sodium, okay, it's a 3s with only 1 electron. Potassium, 4s with only 1 electron. Rubidium, 5s with only 1 electron. And cesium is 6s with only 1 electron. And if we went back and did francium, we would have all this mess, and then the very last would be 7s with 1 electron. All right. Now, if we could put on our thinking caps, if we wanted to do the electron configuration for the element right next to each of these, so say, for example, beryllium. Beryllium would be only 1 more electron bigger than lithium. So what would 1 more electron be for beryllium? Be 1s2, 2s2. Right next to sodium is magnesium. Magnesium would be 1 more electron past sodium, so magnesium would be 3s2. And I could say the same thing going all the way down this chart. So for every single one of these elements, in the second column, the very last entry in the electron configuration would be something with an s2. Now, let's go back to hydrogen. We have to jump all the way over to the other side of the periodic table to find its partner or its next door neighbor. And helium would be 1s2, by the way. But all these others that are in this column would end with an s2. For that reason, the very first 2 columns of the periodic table are often referred to as the S block. They're referred to as the S block elements because the elements in these two columns have electron configurations that end with an s orbital. The very first row ends with an s1 orbital. The second column would end with an s2 configuration. All right, I hope you see that. All right, let's stop right here, and we'll check out what's going on this portion of the periodic table, the last 6 columns. See you in the next video.